In the last lecture, we introduced the theory of special relativity. And this is based on two very simple postulates. The first is a very powerful postulate that implied all of Galilean relativity that we knew about before. And the second is something that forced us to go towards a new theory of relativity, the theory of special relativity. The first is simply that if I have two reference frames, two sets of coordinates moving with respect to each other at a constant velocity, then I can't tell from doing experiments in either of them which one I'm in. I have to actually compare them in order to tell. In other words, you can't tell if you're moving, you can only tell if you're accelerating. The second postulate said that light propagates at the same speed in all inertial reference frames. That's very different to, say, tennis balls. If you throw a tennis ball between yourself and a friend, and then someone drives past in a car, they might see the tennis ball, in fact, go at a very different speed. If they drive at the exact speed that you're throwing the ball, then they will see the tennis ball actually still. Whereas light is always going at exactly the same speed in all inertial reference frames. It seems like that can't possibly work, because if I have a torch, say, and I'm sitting in that car, and I turn on my torch, if I see the light go ahead of me at the speed of light, then someone by the side of the road surely must see it go faster. The only way that can't work is if, in fact, the way that space and time and the way that those two inertial reference frames are related is different to what we think. And in fact, what we then went and did with these two postulates is we went and saw exactly how two moving frames of reference have to be related, and we came up with the Lorentz transforms. And so if we have this standard set where we have one frame moving along the x direction compared to the other at velocity v, then the time, space, coordinates of the dashed frame, the s dash frame, are related to the original frame by this set of transformations. And you can see that they're linear, and you can see that they are not the same as the Galilean ones. The Galilean ones where the time wasn't changed, t dash was just equal to t, and that x dash would just be a standard moving thing. So this factor of gamma wouldn't be there. And the Galilean ones did in fact have that the transverse dimensions were unchanged, as do the Lorentz transforms. You'll note that the Lorentz transforms look like the Galilean transforms in the limit that the velocity is much smaller than the speed of light, because then this term goes away, and this gamma looks a lot like 1, and so we have just t dash equals t and x dash equals x minus vt, and we have the Galilean transforms back. And this is why, of course, the world and our intuition looks like frames transform in a very Euclidean way, whereas in fact they transform in this way. Now we can practice using the Lorentz transforms to do calculations just by showing that they give us the time dilation and length contraction that we discovered in the previous lecture. Let's look at time dilation first. Supposing we have an observer and they're just sitting doing nothing, and so on a space-time diagram, so that's where we plot how they move in space and time. So this would be our spatial coordinate, this would be our time coordinate. They're just sitting still, so there they go. They're going to travel along what's called a world line. And they'll start at some time and position here, and then at a later time, because they're not moving in this frame, we'll have a later time, t equals t1, but x will still be x0. Now we'll simply use the Lorentz transforms to find out what these coordinates look like in the s dash frame. So supposing this frame was moving along, it's going to look like they're moving backwards in that frame. Let's show that. So t dash, if we plug in our t0 and our x0 in there, we're going to get, and when we plug in our x dash, we plug in our x0 and t0 into here, and we get, now the coordinates of this point, the space-time coordinates in the s dash frame are going to be, again, we just plug in t1 and x0 into the Lorentz transforms. Now we don't care too much about the x dash coordinate, in fact, because all that's telling us is that our coordinates are moving backwards. So this object that this frame thinks is at rest, the s dash frame thinks, oh no, it's just sliding backwards. Fine. What we care about is how long it's spent going between these two times. So in this frame, in the s frame, it's taken t1 minus t0. Now in the s dash frame, the time difference is just the difference between the two t dash components, but you note the second term, the x0 v on c squared times gamma, those two terms cancel. And we see that time taken in the s dash frame is gamma times the time taken in the s frame, and so we have time dilation. Now let's look at length contraction. So suppose now we don't just have a point, but a bar. And that bar is of length L. What that means is that the back in the rest frame of the bar, so we'll have S being the rest frame of the bar again and S dash being the moving frame, then the back of the bar is just going to follow a world line straight up from the origin, and the front of the bar is going to follow a world line straight up from the front like that. And so anytime you want to look at this bar and measure its length, you just pick a time here and an equal time, and you look at the distance between these 2 points. Now interestingly, in the S' frame, these 2 points are not actually simultaneous. So these are not the 2 times at which you need to measure the length of the bar. You actually need to measure the length of the bar at different times in this frame, in the S frame, to be measuring the front and back of the bar at the same time in the S' frame. And because that bar is moving in that frame, it matters when you measure the front and back of it. So let's take 1 time here, which we might take to be the origin to make it easy, and 1 time here. So this has coordinates, and this is going to have coordinates. We know it's x equals L because the length of the bar is L. So those are the coordinates in the S frame. And now we're going to work them out in the S' frame. And you can see why I chose the origin, because the transformation there is particularly easy. And you can see that I get a far more complicated version for that. Now what I'm going to demand is I'm going to demand that this time t dash is the same as t dash equals 0. So in other words, I'm going to demand that in the S' frame, these 2 points are at the same time, and then the distance between here and here is going to be the length of my bar. So in other words, I'm going to demand that this equals 0, which is going to also demand that t1 equals LV on c squared. And then I simply plug that into this equation here. And because this is 1 on gamma squared, that means that L' is just L on gamma, which is length contraction. So you can see that the bar in the S' frame is going to look shorter because the distance from here to here is this smaller distance, L on gamma.